It's a great honor to give a talk to you today. I'm Shoji Nakazawa from Toyoshi University of Technology. Introduction. Arch structures are one of the typical structural forms of spatial structures. Since direct dynamic nonlinear response analysis is rather difficult, so we propose a seismic performance evaluation method based on static analysis. Next, we focused on the difference between static and dynamic analysis. This figure illustrates the relationship between vertical displacement and seismic intensity. As you see, the post-yielding range is different between static and dynamic response analysis. When the critical vertical displacement, dz critical, is set by the designer, the critical seismic intensity, d lambda E critical, is evaluated by nonlinear dynamic response analysis. D lambda E critical indicates the seismic performance. A static ductility index, SF, is defined as D lambda E critical divided by S lambda EY, as shown in this equation. We define the static ductility index of arch structure SF as this equation. Here, D lambda E critical is a critical seismic intensity in the response analysis. S lambda EY is a yield seismic intensity in the static analysis. If you can evaluate the value of S lambda EY and SF, you can easily estimate D lambda E critical as well. The purpose of this study is to propose the equivalent static seismic load for static analysis to analyze the yield intensity S lambda EY based on static analysis, and to evaluate the static ductility index SF. Finally, to propose a method to evaluate the critical seismic intensity. Numerical model. This figure illustrates the geometry of an arch model. The span L is 30 meters supported by pin end. For half angle phi 0, 30, 40, 50, and 60 degree are considered. The members are steel pipe. The slenderness ratio is assumed to be 100 and 120. The thickness is defined so that the safety factor against dead load is 5.0. The input earthquake motion are 10-wave artificial motion simulating the design response spectrum specified in the building standard law of Japan. This figure shows the design response spectrum. Next, I would like to talk about the equivalent static seismic load. There are two dominant vibration modes in arch structure. One is the first order mode with large bending moment, and the other is the higher order mode with large axial and base shear forces. Therefore, we use approximate vibration mode based on the continuum theory of arches. These figures illustrate the first and higher order mode based on FM analysis. Blue line illustrates the proposed approximate vibration modes. As shown in these figures, you can see that the proposed approximate modes are in good agreement with the vibration mode based on FM analysis. The equivalent static seismic load is expressed as the sum of the seismic loads of the first and the higher mode. This figure shows a comparison between static analysis and linear dynamic analysis. The response by static analysis generally evaluates the maximum responses by dynamic response analysis. This figure shows the relationship between yield seismic intensity and half-open angle obtained by nonlinear static analysis. As shown in this figure, the yield seismic intensity is larger for smaller half-open angle. In this study, the critical deformation is determined by the maximum vertical displacement, d critical. The value of D critical is defined as this equation. Here, SDY is the vertical displacement at initial yielding in the static analysis, and mu critical is the critical ductility factor. In this study, the values of mu critical are assumed to be 1.0, 1.5, and 2.0. This figure illustrates the critical seismic intensity d lambda E critical corresponding to mu critical. As shown in this figure, d lambda E critical tends to increase with the increase of the critical ductility factor mu critical. And when the critical ductility factor is 2.0, the critical seismic intensity exceeds 5.0 for all models. We focused on the static ductility index. The value of SF is evaluated as this equation. This figure shows a relationship between the static ductility index and the critical ductility factor. The static ductility index becomes larger as the half-open angle is larger, and it is independent of the slenderness ratio. The estimating equation for the static ductility index is expressed as this equation. This figure illustrates the relationship between the coefficient alpha and beta in the estimating equation and half-open angle. From this figure, the coefficient alpha and beta are independent of the slenderness ratio, and the coefficient beta has a linear relationship with the half-open angle. This table lists the value of alpha and beta. Finally, a summary of the study is shown on the slide to conclude the presentation. Thank you very much for your attention.